nesta ocasião muito especial. Eu sou Vítor Cardoso, do Departamento de Física do Instituto Superior Técnico. Mais uma vez, obrigado por estarem aqui via Zoom ou vendo o streaming direto. Este é um evento muito especial para nós. O Departamento de Física do Instituto Superior Técnico celebra 40 anos. São 40 anos a formar cientistas e académicos extraordinários e alguns dos pensadores mais importantes da atualidade, certamente no nosso país. É um departamento único e é uma escola única. Há 40 anos atrás, que foi quando este departamento nasceu, havia uma parte substancial da comunidade científica para a qual os buracos negros eram ainda considerados fantasia. Não era uma comunidade tão pequena assim. Uma coisa de loucos. Na altura, um buraco negro, quem trabalhava em buracos negros era um pouco um sonhador. Mas como eu gosto de pensar que este departamento transforma sonhos em realidade, decidimos hoje, nesta celebração, trazer um convidado muito especial. É o Prémio Nobel deste ano, o Prémio Nobel de Física de 2020. É o professor Reinhard Genzel e foi a primeira pessoa que viu e estudou em detalhe, pela primeira vez, o buraco negro que se alojou no centro de uma galáxia, na realidade da nossa própria galáxia. Este trabalho, o trabalho que levou ao Nobel, demorou décadas a fazer e é um trabalho absolutamente espetacular. Como nem todos os que nos estão a ouvir falam português, eu vou agora passar para inglês. Hello everybody, following this via Zoom or streaming, it's a great pleasure to be here with you today. Somebody once said, I think Nietzsche, that there is nothing we like to communicate to others as much as the seal of secrecy together with what lies under it. I think this is a very appropriate description for why black holes are so fascinating. Their name conjures up secrets and the object itself seems beyond reach. So, well, today we have the immense privilege and honor of having Professor Reinhard Genzel, the 2020 Nobel Prize in Physics, here today with us. Professor Genzel will tell us about the 40-year journey to break the black hole seal. Dear Reinhard, thank you so much for speaking to us. Thank you so much for being here with us. The stage is yours.
Thank you very much, Vitor, and dear students and colleagues. It's wonderful to come and be with you, of course, only in a virtual sense. So the story which I want to share with you today is one which has kept a number of us busy for quite a long time. In fact, for myself, it's 40 years. And as you will see, it's part of a still bigger story, which you're all part of, having to do with general relativity and its extremely rich physics and the universe which is associated with it. Now, this is a story, as you will see, in part of experimental physics. Of course, it's, as you will see, it's motivated by the theoretical predictions of general relativity, but it's a journey which required us to develop instrumentation, ever more complicated, precise, better instrumentation. And it's involved a number of people, including people from Portugal. I'm very pleased that some of them are here today and sharing this with us. And as you see, this is a European collaboration, which in the end relies to a large extent on the so-called Very Large Telescope of the European Southern Observatory in Chile, and where we have unique ways of working. And as you will see, a very important recent culmination of this work has become possible by building an instrument which has never been built before to combine 4 8-meter optical telescopes to a single telescope. We call that the gravity experiment, and that has played a very important role So there's on total about 100 people involved in this. So quite a number of people, students, postdocs, engineers, theoreticians, and of course physicists. So I can't name them all. And in fact, we call ourselves the Gravity Collaboration. Now, the bigger picture we, of course, have is that these things we now call black holes emanated early in this century, when Albert Einstein published in 1915, in December 1915, his theory of general relativity. That theory says that if you have a mass, then it affects the space-time around it in a way that other masses surrounding that feel that change in the space-time, and so in that way change their path, their motions, etc. Now, another important part here, what makes this world of Einstein so interesting and yet so weird, is the fact that the speed of light experimentally is known to be the largest speed at which communication is possible. Now, gravity, as we all know it from the Earth, when we jump up from the surface of the Earth, is a significant thing for us humans. But we can overcome it by taking a rocket. And if you take that rocket with more than 11 kilometers per second or 40,000 kilometers per hour, then the rocket can escape the Earth. Now, if you, in your mind, make the Earth ever smaller, then gravity on the surface of the Earth increases, according to both Newton and also Einstein, such that if it is 1 centimeter in diameter instead of the 6,000 kilometers, the gravity is so strong that the escape speed of the rocket now all of a sudden is the speed of light. And indeed, that means that light cannot escape. So that's where, if you like, one of the aspects of the black holes came from. Now, that was the theory which already a year after Einstein's work, a first solution was found for a very simple idealized spherical distribution by Carl Schwarzschild, whose image you see on top there. 50 years later, another solution was found by Roy Kerr with a blue shirt, blue jacket, for a rotating object. But of course, these are highly idealized mathematical solutions. And the questions in the many years between the first invention and then the 1960 was, do these things actually exist in the universe? Do they play a role? And if so, what? And so the story which I want to tell you is, in fact, that story from 1965 onwards, when all of a sudden general relativity became a very important part of astronomy and space physics in order to understand objects which were then found. And these objects are now called quasars, quasi-stellar radio sources, which were discovered as radio-emitting compact objects in the 1960s, and optical astronomers then found that they looked like stars, very compact, dim stars. Yet when you looked at their optical spectra, then in those spectra, you would see spectral lines, which were very well known in their ratios of wavelengths, but all redshifted by about 16% in the first object, which Martin Schmidt looked at with the Palomar telescope. 16% means that that object was several hundred billion, 700 million light years away. And so the speck, this dim little speck, is actually an extremely bright, compact emitter of light with a total luminosity of 1,000 times that of the Milky Way. So the theorists in the 60s then started immediately thinking about what could that be? And remarkably and paradoxically, the black holes came up. Because if you have a black hole, I explained already to you that within a certain region we call the event horizon, light cannot escape for the reasons I explained. But when you have material falling into it, on the way before the material disappears into the black hole, it can convert its momentum, its energy into heat. And in that fact, emit about up to 40% mc squared, which is the maximum amount of radiation which a body of a mass m has. So that's how the quasars came in as a hypothesis to explain the massive black holes came in as a hypothesis of explaining the quasars. So how would you possibly prove that? Well, you would have to make measurements very, very close to the event horizon of a quasar, which is in solar system scales, and measure the space-time there. Now, the quasars are very far away, as I explained, so you cannot really do that. So in a very famous paper in the 1970s by Bell and Rees, they speculated that maybe these massive black holes, which you would need of hundreds of millions of the mass of the sun, in the cores of galaxies, which what quasars are, maybe they exist everywhere else. It's just that only a few, or a very small fraction of the time, they accrete material in amounts which make them light up as quasars. So Bell and Rees actually proposed that such, if that's correct, such massive black holes might also exist around us in the Milky Way. And that's the story which I will tell you, which has now led to this year's Nobel Prize, given in one half to Andrea, I guess, and myself, for showing that in the center of our Milky Way, as proposed by Bell and Rees in 1970, there is indeed an object which we now can show is likely, very, very likely, a massive black hole beyond any reasonable doubt. Now, there's a third person who shared with us the other half of the Nobel Prize, and that's Roger Penrose, whose picture you also see on the left side. Now, Roger actually showed that these very idealized configurations, which Schwarzschild and Kerr looked at, are not necessary to understand the existence of black holes, and therefore, even under less idealized situations, black holes might form. And so he actually laid the foundation to believing that these systems might indeed be realized, and in fact also that you can extract energy out of them, surprisingly. So black holes in that sense are not as black as you might think. Now, this is work which, as you will see, happened in the last 40 years, but remarkably, 100 years after Einstein's theory, several things have been happening to move this whole field forward in a very rapid fashion. One is the discovery of the gravitational waves only 3 years ago, also in the meantime recognized by a Nobel Prize, which we believe is the merging, the in-spiral and merging of two stellar black holes. So not like the object I will tell you about today of a million or millions of solar masses, but of about 10 to 30 solar masses. And then finally, last year, another approach was made by millimeter observers, taking what we call intercontinental interferometry to make an image at 1 millimeter wavelength of a nearby but very, very massive black hole in the core of the Virgo A or M87 elliptical galaxy, which, as you see, has sort of a ring of bright millimeter emission around a dark patch. That dark patch, in fact, is expected theoretically, if there were a black hole, because the photons very close to a massive black hole, according to Einstein's theory, also would go on curved orbits, not just particles. So you see, we are in a remarkable situation that after 100 years, now more than ever, the experimentalists are coming up with evidence, ever better evidence for these objects, and understand now what their role is in the universe. And at the end of the talk, I'll show you where that might go to next in this story. Now, when you travel into the center of our Milky Way, you encounter immediately one problem. We live on the outskirts of the galactic disk, but as we travel towards the center, you see there are these dark patches. These dark patches are dust particles in the interstellar space, which dim the light very much so towards the center of the Milky Way by about a factor of 10 to the 12. So you can actually not see the center of the Milky Way in the visible, and you have to go to longer wavelengths. And so the pictures you see here of the central few light years of the Milky Way, in fact, is infrared radiation. You can see it also in the radio and also in short wavelengths like X-rays. So the Milky Way exploration started in the 70s when radio astronomers looked at the galactic center, and they found swirls of gas, which in the central image there are these pink and green filaments. It turns out these are, the green is neutral gas, and the pink stuff is ionized hot gas. And in the middle of this region, in the star cluster, which you see here blue, is a very compact radio source, Sag A star. And the radio astronomers over the years got ever sharper images of that radio source. We now know that at 1 millimeter wavelength, it is a mere 10 microarcsecond, or a few tens of microarcseconds across. So indeed, again, consistent with what Lyndon Bell and Rees had proposed, X marks the spot, so to speak. That's where you would say that's the center of our Milky Way. Now, how could you then, get close to a sort of a evidence that this indeed is a black hole? Now, the first attempts were made in the 70s in the infrared by a Nobel laureate named Charles Townes and his students. Charlie Townes in Berkeley then had previously gotten his Nobel Prize for the invention of the laser and the maser, and then later on moved to California and formed a group in astronomy. And they developed instrumentation in the infrared, which allowed them to look at these gas clouds, which I explained to you. And it turns out that these gas clouds are actually moving in very considerable fashion, such that from the magnitude and the direction of the motion, you can say something about the mass, which is in the center, typically on the scale of light years. So in fact, the green stuff is on a more or less circular orbit, tipped with respect to the line of sight, while the pink stuff, this ionized gas, which comes closer to the center, closer to Sag A star, which is right here in the center, moves with very high speed. The speeds are several hundred of kilometers per second. So if you take Newton and calculate from that motion as mass, assuming that this gas is in virial equilibrium, well, you get a mass of few million solar masses. So by the end of the 1980s, which I call the first phase, and I had joined at that time the Berkeley group and was working with Charlie, first as a postdoc and then as a faculty member at UC Berkeley. We knew that within about a fraction of a parsec or a few light years, there was a mass of several million solar masses, and that this mass could not be explained just by the stars which are in the center. The stars would be, a few 100,000 solar masses. in this region. So clearly there was an excess of mass. Now, is that a black hole? Well, we believe so, but in science, of course, you have to convince others. And in terms of this event horizon, which I mentioned to you, within which light cannot escape, these filaments here are moving at about 1 million times the event horizon size. But that's far away, still enough to be influenced by the gravitational force by the black hole, but far away outside. So you might think of other configurations other than black hole. So it was, at this point, you know, tentatively interesting that this might be a black hole, but not sufficient. So how would you do better? And so in the beginning of the 90s, it became clear that we needed to look at the stars and not just at the gas, and that we needed to come closer. And we needed to build instruments. And so, in fact, this project over the years is very much involved and connected with tremendous progress in detectors, in so-called adaptive optics to remove the blurring of the images by the Earth atmosphere, imaging spectroscopy, which we call integral field spectroscopy, and the capability of actually sensing the distortions of the Earth atmosphere at any point on the sky. And we do that, as you see in the middle picture, by shooting laser guides, stars, into the sky. So this laser is getting focused in the upper atmosphere, where there's a lot of sodium from meteorites coming down, and that then is used to generate an artificial star right next to the object we want to look at, say, for instance, Sagittarius star. And so this kind of technology, plus the big telescopes, which became possible in the 1990s, the Very Large Telescope in Europe, and the Keck telescopes in the United States, Subaru, and many others, really were the key to go the next steps. And in this next step, two groups were leading the pack. One, the group here in Munich, together with colleagues, and another one led by Andrea Ghez and Eric Becklin at the University of California, Los Angeles, using the Keck telescopes. So as I said, what we did, we were looking at the stars now, and not at the gas, and on smaller scales. So the green cross you see is the position of Sagittarius star. And the green circle is 1/2 of an arcsecond. So that's already much better than you can do with normal atmospheric disturbed seeing. And that's because we had initially so-called speckle imaging and then adaptive optics. And what you see here are images of the stars near Sagittarius star on 3 occasions in 3 different years, in red, in green, and in blue. And you can see that there's one star right next to Sagittarius star, which surely is moving from year to year to year. And if you look at the upper right, that's 2,000 kilometers per second. I mean, the Earth moves around the sun with 30 kilometers per second. So that's, 100 times the speed of the Earth around the sun at this point. Now, is that motion indicative of a point source? Because we want to prove, of course, that there's a point source. Well, I remind you of the Kepler's laws. In the center of our solar system, we have the sun, and then we have the planets on more or less circular orbits. And Kepler's laws tell us that the further out you go, the slower the motion is. So look here, when you go very close to the cross, the motions are very large, obviously. The prism effect is very large. As you step out, the prism effect gets obviously less, so that out here, the images are almost white. That's a qualitative way of saying these motions indeed look like the motions around a compact object. And so from the statistical analysis of such data, we and the Keck group a little later were able to say that a 2, 3, 4 million solar mass object must be within the central light month. So this is already 5 times closer, 6 times closer than we knew from the gas. So must it be a black hole? Well, it probably could be one, but still you could think of other configurations. So for instance, you could imagine that if you put 1 million neutron stars into the central region inside of the circle, well, the stars would also see this concentration of neutron stars and would move in a similar fashion. So we had to still do better. And how can you still do better? Well, still closer. And not only statistical measurements, but actually individual motions of stars, orbits. Well, what kind of orbital timescales would you expect? You can easily calculate the orbital timescale of a star within a light month, and you will find it's hundreds of years if it's in a circular orbit. Well, hundreds of years is a little long, even for long-lived humans. So that is not a good proposition. But then, in fact, nature helped us. Nature helped us by giving us stars which were so close, unexpectedly close, that some of them were on orbits of only tens of years. In fact, one, as you will see, our best one, has an orbital period of only 16 years. And this star, S2 or S02, as our colleagues at UCLA call it, is on an orbit which is highly elliptical and approaches Sagittarius star to within about 17 light hours. That happened the first time in 2002, and both the groups saw it. So by 2002, we knew there is a star which comes down on scales of the solar system, 3-4 times the Neptune's orbital radius. And so if you now calculate the motion, by the way, at that point is about 8,000 kilometers per second. So you take that 8,000 kilometers per second and the distance of 17 light hours, and you can calculate the enclosed mass, and it comes out to be 4 million solar masses. So the same millions of solar masses which we had seen with the gas in the 1970s and 80s, and the same mass which we had seen in statistical fashion in the 1990s, must now be enclosed within 17 light hours. So by 2002, 2003, that work of the two groups, especially since we agreed, convinced many people that indeed this is very likely a black hole. But must it be one? Well, it certainly left little loopholes unless general relativity is wrong. But how do we know that general relativity is correct? So by 2003 or 4, a number of us here in Europe said, well, this star will come back in 2018. We knew its orbital period to be 16 years. Can we not build an instrument which by that time can see the effects of general relativity? And that led to the formation of the Gravity Consortium, which has groups from Germany, 2 Max Planck Institutes, University of Cologne, the University of Grenoble, then Porto and Lisbon, and ESO, the European Southern Observatory. And so we formed a team to build an interferometric device to look at the next pairing. So by 2017, just before the star returned, we knew the mass of the black hole pretty well to, say 5%, 10%. And we knew that this mass had to be within 100 Schwarzschild radii. So that's a very different constraint already from early on. So you could imagine at that point sort of a speculative object called a boson star and a few other things. Every other possibility would not be long-lived enough. So then we were busy for 10 years building gravity. So here you have the Paranal Observatory in Chile in the Atacama Desert. You see the 4 8-meter telescopes, And underneath this platform, there are tunnels through which one can send the light from the big telescopes down to a laboratory, which you see in the center, where you can combine the light. And this is what we did. We built an instrument to combine that light, which we call gravity. And I want to show you what we had to do in order to make that a success. So this experiment was led by Frank Eisenhower and our gravity team, improving the resolution another factor of 30 and the astrometric precision by factor of 20 or so. But that's not easy to come to, and I want to show you how this actually goes. This is a movie we made, which we call the last microseconds of a tortured photon. So here comes your photon hitting the Atacama Desert, and there's the VLT. So it's the primary, the secondary, and the tertiary of the telescope. So now we need to bring it down through a number of mirrors, quite a number of mirrors, to the basement of the telescope, where we then actually have adaptive optics to correct for the blurring of the Earth's atmosphere. So that's here where we're sensing the distortions of the Earth's atmosphere. And then we bring the light together. We do this for each telescope. And then we bring the light together in the tunnels, also correcting for the geometric path length difference. We have to do this to about 10 nanometers precision. And then finally, we bring the 4 beams from the 4 telescopes together in a single instrument in vacuum and also at very low temperature in order to minimize any distortions and disturbances. So now in this compact environment of this duo, we have to do some more preparation of the 4 beams. And in particular, in order to make this a success, we have to split the light in 2 ways. One from a star next to the object, and then from the object itself, because the Earth's atmosphere is moving around all the time, and its coherence time is only a millisecond. So to make the measurement of the very faint stars, we have to repair and measure the effects of the Earth's atmosphere on this millisecond timescale. And then finally, once you've done this, we can bring the light through single mode fibers. Here you see them from the 4 telescopes. Here we can make the corrections for the distortion of the Earth's atmosphere by bending the modes. We can also actually distort the waveguides in order to correct for polarization. And then finally, at the very end of all of this, we can combine the light in a microchip, very much like in radio astronomy, in an optical microchip developed for communication industry, which is a size of about a 1 centimeter strip of silicon. You see it there on the right side. Coming with 4 beams, you combine the light into all the different combinations. You come out with 24 outputs. Finally, put the thing through a spectrometer in order to spread the light, and then put it on a very low noise detector. So all of this you have to do. In addition, you have to send out lasers back to the other way in order to measure the distances to nanometer precision. So that's gravity. It's a really complicated instrument. Probably one of the most complicated instruments ever built in astronomy. Not as complicated as the gravitational wave experiments, but somewhat the same. So now we can measure the incoming star, which by the time we had the interferometer experiment ready in 2016, had another year to go. And the symbols here now in blue are the measurements from the interferometer, whilst the black measurements are the adaptive optics measurements. You see how precise we can measure things. We can easily see now the star S2 separated from the also visible black hole. The black hole radiates as well, at least in a variable fashion. Typically a few hours per day it's on. And so here you can see the time around Perry, and the different points are the measurements with gravity on different days. So here we can see the motion of the star around Sagittarius star, which is up here near Perry in May 19th, 2018 on a daily scale. So that tells you how precise we can measure. We can also sense the spectra through integral field spectroscopy and measure very precisely the Doppler motions. So we can see 3 motions, 2 on the sky and z velocity, as well as 2 coordinates on the sky. And so if you do that and you measure the orbit, then you can, from one orbit, deduce all the parameters you need to measure the mass, the distance to the objects, and you can ask the question whether there are deviations from Newtonian physics. And indeed, by summer 2018, we already had the first such effect, which is called the gravitational redshift. The gravitational redshift happens because when the star is very close to the black hole here near Perry, the gravitational attraction, of course, is a maximum. So the stellar light to come to us has to climb out of the potential well of the black hole, and so it loses energy. So compared to Newton, where this effect would not be there, you can look at the difference in velocity space. So this is a relative change in velocity between Newton, which on this scale is a flat line. So you remove the elliptical motion of the elliptical, the Kepler ellipse, and we just look at the differential to what general relativity would predict, and that's the blue line. And red are the data points. So you can see we have clearly at a high significance seen that gravitational redshift at about 25 significance levels. A year later, our colleagues at UCLA also saw the effect. So that's the first indication, indeed, that general relativity holds around an object of 4 million solar masses. And in that sense, 100 years after Einstein, where similar effects were looked for, in 1959, in fact, the Pound-Repka experiment showed the gravitational redshift in the laboratory for the first time. So now we can do it at a distant laboratory of a black hole. Another effect we can check here is the so-called local positional invariance in the equivalence principle. That basically says that if you have different atomic clocks, and in the spectral lines we have hydrogen on the right side and helium on the left, then they should see the same effect. So you should see the effects of the gravitational redshift in the same way for the 2 atomic clocks, and we do. So that tells you that the atomic physics is not affected by atomic physics does not affect the gravitational effects. The next effect, which you would expect to see, is a deviation from a pure ellipse or a circular motion. So if you have Newton and you have a central mass like the sun and a star or a planet around it on an elliptical motion, and there's no other object nearby, then the object would stay constant in space. The elliptical motion would always be the same. Not so in general relativity. That was, in fact, an effect which Einstein predicted and was first seen then in the Mercury orbit in 1919. So, very shortly after the theory was published. And on the right side, you can see in the x coordinate and in the y coordinate, in a differential between general relativity and Newton, what you would expect for the orbit of S2. So if you set the phase of the orbit to 0 here at Apo, which is at this point here, then what you would expect is that this precession of the Schwarzschild precession should be very slow because the orbit is very elliptical, but then be very rapid near Peri, which is right here. So more or less a kink. And it's more or less only in right ascension. In angle, it's basically so that you go from one angle near Peri rapidly to another angle. So that's what you would expect from general relativity. And that's what we saw in our data. So you clearly see that beautiful kink, from a sort of a constant position angle, and then basically going to another angle, or here this change in the angle. So clearly, with good significance, we can also see the Schwarzschild precession, which is a harder thing to do than the gravitational redshift. Now, we are still with this star at Peri, about 1,000 Schwarzschild radii away, even at Peri. Although it's so close that the star moves so fast, can we somehow get still closer? Now, I mentioned already that the black hole itself is visible in the infrared, also at X-rays, also at radio, and in infrared it's highly variable. You see a trace up there. It's varying all the time, typically very faint, but sometimes very bright. And the explanation theorists have proposed for this strong variability is that in the central region, you have the hot plasma of about 100 million degrees, and you have magnetic fields. And from time to time, magnetic fields get entangled with each other and do what we call reconnection. And that reconnection transfers energy to the electrons in the central region, making them still hotter. And that is a localized effect. And that could create hot spots in the infrared such that you could see, so to speak, a motion near the event horizon. And indeed, 3 times in 2018 at the bottom, we saw this effect. Very much in the same direction on scales of about 3 to 5 times the Schwarzschild radius, or 6 to 10 times the gravitational radius, on orbital periods of 40 to 50 minutes. So if you convert that into a velocity, a coordinate speed, that's about 0.3 the speed of light. And indeed, that is the orbital speed you would expect in general relativity at so close to the event horizon, around a 4 million solar mass object. So we have now, at least with first measurements, we need to do more in the future, come very close. And I'll summarize that in the next slide. So that's the physics. Let's talk a little bit about the astrophysics of all of this. What would you expect if you had a massive black hole in a stellar cluster? Many people have thought about this. And basically what happens is that the stars surrounding the black hole would get attracted to it and form what we call a cusp. So on the right side, you see the distance in logarithmic units. And here is the density of material. And so the prediction is that the density of stars, at least old stars, should get ever more peaked near the big black hole. And in fact, from time to time, every few tens of thousands of years, a star even has the bad luck of falling into the black hole. What do we see? Well, we do see such a cusp, but it's young stars, remarkably. So that's not what you would have expected, because they don't have enough time to migrate in there, whilst the older stars actually do not show much of a cusp. So that's actually quite a bit of a puzzle. And so this star cluster is not really what we would have expected. Also, there are young stars there. Right around the big hole, there's about 100 O stars and 200 B stars. That's not what you would have expected, because the tidal forces of the big black hole should have prevented stellar formation. So that also was a surprise when we first discovered it. We now think that comes about because sometimes every few million years, a cloud falls into the center, gets trapped, and then basically cools until it can form stars, and then you see this circular motion of a disk structure of stars. Now, theoretical consideration allow that in this cusp there might also be more massive objects, certainly stellar black holes, which we cannot see, but even also, intermediate mass black holes. In fact, how do we know that the black hole is a single black hole? It could be a binary black hole. So in fact, the motions we've done they're measured with gravity are very valuable to test the hypothesis that this is a single object. And in fact, we've analyzed the data now to the extent that we are certain that within the central region, the S2 orbit, basically nothing more massive than maybe 100 to 1,000 solar mass black hole might fit in, or several stellar black holes, but not an intermediate mass black hole. That's very important for gravitational wave studies in the future, because they, of course, are very sensitive to in-spiral effects. So now, after 40 years of research, we've come a long ways. I showed you at the beginning of the story, we were just seeing at the sphere of influence, and we were beginning to see on light year scales the few million solar mass object. And we sort of basically moved slowly inwards, ever better instrumentation, ever further in. And now we've come to a few times the event horizon size. We know the mass of the black hole and the distance of it now to a fraction of a percent. We hope next our millimeter colleagues will see this shadow. If you measure the ring of the size of the shadow, but since we know the distance, that's a first order a check on general relativity right there. If we can see stars further in still, which we're hoping to do by upgrading gravity, well, then we might measure the spin and get still further. So we are not done, actually. We are not done. This story is a story which keeps physicists excited. In fact, if you look at the number of publications on the subject of black holes, it's an exponential to a good extent, about as exponential as the growth of the COVID virus on Earth lately. So if you parameterize, in fact, this issue in terms of the so-called no-hair theorem, that is, if you take the Kerr spacetime, which says that you only need two quantities to describe a black hole, the mass m and its spin a, then you can from the theory derive all higher multiple moments. So for instance, the quadrupole moment q, and this little epsilon there, which is a unitless number, should be zero. With other words, we say that the black hole has no hair. It's a very simple object. No hair, no mountains, no dents, no nothing. So the question is, how well do we know this? And in fact, Vito Cardoso has written a nice review to show that the present measurements, so for instance, the in-spiral from the gravitational waves, but also the hotspots near which I've shown you, show this epsilon to be less or equal on the order of unity. So we are very consistent with general relativity and the Kerr spacetime, but we're not yet, able to say it must be that. We cannot say that there couldn't be any deviations. So we need to work harder. So I mentioned already the measurement of of a ring, which the Event Horizon Telescope might do. That might push it down another factor of 2. If we see faint stars and get the spin, maybe we have another factor of 2. If you can combine all of this, then we might get all of this at, 10%. If there's a pulsar which you can measure very accurately, then, same order of magnitude. Finally, I would say the ultimate experiment will come with the next generation big telescopes and an experiment in space to measure the in-spiral of a stellar black hole into a massive black hole with the so-called LISA experiment. So, as I said, this story is by no means over, and there's lots to come. And we hope that for another 40 years, there's lots of new physics, and maybe we find deviations from general relativity at one point, which you would expect certainly on the smallest scales, but not necessarily, of course, on scales which are accessible to us. Thank you very much.
Thank you, Reinhard. This is really an amazing journey. I have to confess that being a theorist, this still looks like science fiction to me. It's really amazing. So we have time for just a few questions. I think José Lemos has one. José, can you ask the question?
Yes, Reinhard, thanks very much for the talk. I'm a professor at IST, work on black holes, physics and astrophysics of black holes. First, I would like to congratulate you and your team for the great work you have been doing, proving that there is a black hole in the center of our galaxy. And of course, many, many congratulations for the Nobel Prize this year. The question I would like to put is the two teams, yours and the Andrea Ghez team, have been working with the black hole at the center of the galaxy. I imagine that the instruments you use and the instruments that the Ghez team uses are different. So are you able to cross your results with the results of the other team? And if yes, do the observations give the same results in detail within errors, of course? For instance, does the other team sees the perihelium, the general relativistic effect of the perihelium, and so on?
Okay, so the answer is the agreement between the results of the two teams, I would say, are remarkably good over the years. If you look at them, since the 90s. I mean, we started with that, and the first statistical work when the Keck group came out, that was within the uncertainty the same. We both saw the first peri and the mass determination and the orbital determination was basically identical. And I would say throughout this whole period over the last 20 years, very rarely did we have major disagreements. Now, of course, the situation is now slightly different in that with the interferometer, we have, about 10 times better astrometry. That is unfortunately critical near peri, because as I've shown you, when you're near peri, with adaptive optics, even with an 8 or 10 meter telescopes, the images of Sergei star and S2 are confused. So confusion is a unfortunate effect for even the 8 meter class telescopes, and in particular near peri. So in fact, if you look, we've taken 8 meter adaptive optics imagery during the entire last peri as the Keck group did, and if you compare our 8 meter AO stuff to the interferometry, you can see the confusion very badly. So that makes the accuracy of the measurements not good enough for the Keck group to see the Schwarzschild precision, at least not near peri. So what they are hoping for is that their reference frame is now stable enough that they see it at the next uphole. The effect at Apo is about 6 mili-arcsec shift. That should be able, if you have a good stable reference frame, you should be able to see that. But you will have to wait another 4 years or so before they can actually get to that point. But I would say, generally speaking, the two agree to the extent you can expect it. I mean, the gravitational redshift certainly is in good agreement. The distance is currently not, and we are trying to find out why that might be. There is, of course, the issue of systematic effects versus statistical effects. And, you know, it's easy to report statistical effects. It's much more tricky to find all the systematic effects. In fact, we are about to publish another gravity paper where we are publishing a systematic effect which affected the distances at the 0.6% level. Once you remove that, then the distances are always the same. But I mean, it's a tricky business to go below 1% accuracy.
So we also asked high school students for questions that they might want to ask. We got just an extremely large number, all of them excellent questions, some of them really hard to answer, I think. So we selected just a handful because we don't have time, almost arbitrarily, almost. Now, the first is from José Costa, Laura Nunes, Mariana Bernardo. They are from Latino Coelho School, and Carolina from Jaime Moniz School. And the question is the following. Do black holes have any influence in the evolution of the universe or of galaxies? And also, is there a way that we can use to extract energy from a black hole? You're muted, Reinhard.
These are excellent questions, and in fact, I can tell you that some of my more astronomy colleagues have said, "Well, look, Reinhard, it's fine that you're trying to test general relativity, but we know that general relativity is correct." Much more interesting, in fact, is the work you're doing with black holes in the era of galaxy formation. Because that's something we also do. And there the story indeed is, and we have found that out over the last 20 years and gotten to an ever more robust picture, that black holes and massive black holes and galaxies have led a symbiotic life. In the early universe, when the universe was smaller, there was much more gas in galaxies. And there was much more gas falling into galaxies. So galaxies were growing very rapidly. And the same gas which would form stars in the galaxies would also feed the central black holes. So they were growing also. So that means that the probability at that time for an object to become what we now call a quasar was much, much higher. In fact, I would say about 10% of all galaxies 10 billion years ago, at the peak of galaxy formation efficiency, had central objects with quasar-like luminosities. And that meant that the energy feeding back into the galaxy through radiation and also gas outflows was very, very substantial, and thereby, in fact, controlling and affecting the life of galaxies, turning them from what we call star-forming disks to boring, passive, elliptical galaxies. So the answer to this question is absolutely. We have seen that these massive black holes have played just an incredibly important role in the evolution of some galaxies. Fortunately, not our own, because if that would have been the case, it could very well have been that the sun would have never come together and the Earth would have never formed. The second question is also important, absolutely. And in fact, Penrose, the theorist who shared the prize with us, worked very hard on this problem. And we believe it's a very important effect to generate jets. So if you have strong magnetic fields, and in fact we have good evidence from our work that the galactic center has very strong central magnetic fields, then of course the ionized gas particles are basically tied to the fields, and the rotation of a central black hole would rotate the magnetic field structures around, and thereby juggle the gas and accelerate it outwards. So in fact, you can tap the rotation of the black hole to generate jets, which is a very famous effect, which Roger Blandford and Snayak proposed in the 1970s. And in fact, Roger this year got also a big prize, a Shaw Prize, amongst, one of which was the fact that his work, in a way, has become extremely modern again, because we're beginning to be able to test these kinds of effects.
So Karina Lage from Colégio FANOR asks, what exactly led you to start looking at the center of the Milky Way? What got you started into the business?
Well, I described to you at the beginning of the talk that after the discovery of the quasars, Lyndon, Bell, and Rees made this very important proposition. In order to measure the space-time, you have to come closer. You have to come closer, and they made the hypothesis that black holes are everywhere, which we now know is true. So including the galactic center. And so then the galactic center became one of several test grounds to see these black holes. And in fact, we now have it, that's our best laboratory. Nevertheless, nearby galaxies also are being used for similar evidence. And in fact, there the evidence is weaker, but still it's quite present. So the galactic center, in that sense, as a laboratory, was obvious once the Lyndon, Bell, and Rees proposal was there. It was just a matter of doing it, okay? And that was the difficult part, doing it and actually getting close enough.
So Marta from Jaime Muniz School and Pedro Loureiro from São João de Brito ask a really interesting question, which is, you've been describing the journey to the center of the galaxy where there's a gigantic black hole. But how exactly did the black hole form? Where did that black hole or others come from, and what happens after they form? Do they die?
All right. So the growth of black holes is something which in part we understand pretty well, and I've described it already to you, which is when the black holes already have masses of, say, a few 100,000 or a million solar masses, then they tend to dominate the gravitational potential in the nuclear regions of the young galaxies. And then indeed the gas which happens to come close into the central region inevitably falls in, and then leads to further growth of the black hole. So that's the story which dominated the step from, say, 100,000 or 10,000 solar masses to the billions of solar masses in the big elliptical galaxies. The more difficult issue is how they grew from initially, when there were no black holes, to this sort of 10,000 solar mass regime. And there's lots of speculation. It must have happened early in the universe. So we must look backwards in time, take the time travel, look at the earliest galaxies and see what happened. Was it because in these earliest galaxies, stars formed which were very, very massive? That's one route, because there was very little in terms of cooling from heavy elements. And so then the typical early stars are hypothesized to have much more mass than the biggest stars we have now, which is 100 solar masses. So then you could start with maybe 100 to a few hundred solar mass seed black hole. Another option is to build a dense star cluster, and that would eventually collapse to, again, an object of maybe 1,000 solar masses. and then grow from there on. So there's various options have been proposed in the literature. We don't know at this point which the right path is. Now, the current evolution of black holes is beginning to be more and more boring, if you want to put it this way. And that is because the probability of gas getting into black holes is less and less, because the universe is expanding. It is expanding in an accelerated fashion even. So as we go to very large times in the future, well, there will be no growth. And so you will have these big black holes sitting there and not doing anything anymore. Nobody will be a quasar for a short period of time. Well, now, of course, as many of you know, there's one thing which might happen, and that's Hawking radiation. So Hawking has made the thermodynamic point from quantum theory that near the event horizon, the uncertainty principle allows a splitting of a virtual particle into one which falls in and one which actually finds itself outside of the event horizon. That's a very, very rare process for a big black hole. And so the loss of mass due to the Hawking radiation for these big black holes like the one in the Milky Way center are so slow that there is absolutely no hope to see that. I mean, we cannot, I don't see any practical way to see Hawking radiation from stellar or big massive black holes. So that's a question to black holes which are very, very small, micro black holes. They could exist, but they have not been found yet. And so at this point, Hawking radiation is a purely, at least from my point of view, Vito, you might have a different point of view, it's a purely speculative effect, but of course, extremely interesting theoretically, because it's connected to another issue, which is the information of what fell into the black hole, where the classical world of Einstein would say, well, whatever fell in there fell into the central singularity, and nobody knows whether it was trucks or planets or rockets or whatever. And the quantum theory who would say, wait a second, all the quantum numbers are still preserved. And so that information should be there somewhere.
But
so
actually, Reinhard, let me take that to merge two questions that we have here related to smaller black holes. And these are questions from two students, Marine Ferreira from São João de Brito and Rodrigo from Jaime Moniz. And the questions basically are the following. We know that massive stars collapse to black holes, but why do stars like our sun don't? And if they don't, so you were just telling us that maybe there are micro black holes. So how would those form, and how would we be able to look for these guys? I mean, you told us how we look for big black holes, we look for matter, we look for light from, how do we go around looking for these small guys?
Right. Okay, let's start with the question of, the question about the sun. Will the sun become a black hole? And the answer is no. What will it become? Well, it'll be very likely a neutron star. So basically the point is, at the end of the lifetime, what we call the lifetime of a star, what happens is that the star runs out of hydrogen, which it can fuse into helium. And, if it's a little more massive, it runs out of helium also, et cetera, et cetera. So in the end, it cannot generate any energy anymore, which generates pressure. And so then you have gravity, which pulls the mass of the object inwards, so it collapses. Well, but there are other forces, nuclear forces, the weak force, et cetera, and that is what stabilizes, relatively small stars like our sun. You have to be more massive than, say, 8 or 10 solar masses before the nuclear forces don't preserve the eventual collapse to a black hole. But it could be through other processes which we don't understand, possibly even during the Big Bang, that there are these miniature black holes around, and there's in fact a lot of speculation. I would say an increasing amount of speculation, at least from my point of view, because of another effect, which is dark matter. Dark matter is something which we observe through, again, the space-time effects on large scales. We do this in galaxies at high redshift, for instance, or in clusters of galaxies, or in the cosmic microwave background. And so there you have evidence that there is material around which is not normal material, but 4.5 times as much as normal material, which we call dark matter. It's not visible. And the speculation had been it's an elementary particle, very massive elementary particle without a charge. So we can't see it through electromagnetic or strong forces. And so, you know, our laboratory physicists in deep tunnels have tried to find it and have worked very hard, ever better, haven't found anything. And we all are getting worried why they're not finding anything. So are you worried, Vitor, that we have to introduce miniature black holes?
I'm not worried, but I would like to find them, yes. But so, Reinhard, I know you have an appointment with reporters, so let me go to the last question, because it's also, I think, perhaps the reason why your discovery, your study, your prize is so important. This is from Maria Leonor from the Colégio Luso Francês. And the question basically touches on the very notion and nature of black holes. She says that she read in the National Geographic that if you take a spaceship and hover over a black hole at the center of our galaxy, your black hole, then a minute in that spaceship could be 1,000,000 years on Earth. And the question is, how can a black hole affect the passing of time? You know, the fact that we're looking at an object that's really a hole in the universe where distortion, space-time distortion is so huge. Do you have an intuition on how?
Yeah, I mean, these effects are, you know, already germane to special relativity. That if you have two systems, you know, at very fast speeds, moving relative to each other, which are trying to communicate. They are trying to communicate through light, and then immediately the effect of communication problems arise because the light ray you emit from one in the reference frame or from one to another suffer from time dilation effects, and so it's not only general relativity which has that property. It's also the effects of general relativity. It's just communication gets distorted at high speeds because there's a speed limit.
That's right. Reinhard, I would like to thank you for the really fantastic talk, for the fantastic achievement, and for sharing all of this journey with us. Thank you so much. It was a big privilege.
Thank you. It was great to have been there, and I wish I could have been there in person.
I hope we still have time. Thank you so much, Reinhard.
Bye-bye. Okay. Bye.
Thank you.
So what happens next? I go to another site, right?
Right.
Yes, I think you need to connect now.
Thank you have the links.
So I leave here and go to another site.
Yes.
That's correct. Yes.
Hi, Paolo.
Hi. Thank you.